we have a situation like this. If you are hanging a stone, the weight of the stone is actually 20 Newton in air. Okay, so the actual weight is actually 20 Newton. In this case, when you put into the water, when you touches the water a bit, okay, not really a lot, you touch a bit, you touch a bit with this, and you realize that the reading becomes 14 Newton. So it shows that the upthrust is actually equals to 6 Newton, perhaps. So what we can say about 14 is the apparent weight of the stone. Okay, the actual weight of stone is 20 and the upthrust is 6. But this situation is different because here the weight of the stone on the water, this one is going down at 20 Newton and the upthrust is actually 20 Newton. The upthrust changes. The upthrust depends on how much amount of liquid you displace. You see, this one apparently takes up more space and move the water away more. Okay, take out the space more, kick the water away more. So here's 0 because this one has become loosened and there's no more tension. Then when there's no more tension, it's just 0 Newton. So in this situation, we can say that the system of particle or object is upthrust equals to the mg, okay, or w if you like to call it. So this brings us to another principle. Not another principle. This principle is Archimedes' principle states that the buoyant force acting on an object in an upward direction is equal to the weight of the liquid being displaced, not displayed. Okay. So upthrust, not Fu, upthrust equals to weight of the liquid being displaced. Okay, if you have a container like this and you put a stone and then the water comes down and then you measure it, you measure the weight, it is actually 6 Newton. It is actually 6 Newton when you have weighed your stone to be 14 and then you realize, how comes this is 6? So it really shows that the upthrust is 6 Newton, and also like what we said just now, like what we mentioned just now, here 20 equals to 20, upthrust equals to the actual weight of the stone, okay, fully supported. So you feel almost no weight at all. This situation C, why don't you just imagine yourself floating on the water? You feel like no weight at all. Does that mean that you don't have an actual weight? You have an actual weight. It says that your actual weight 20 Newton going down is supported by 20 Newton moving upward towards you. So you still have your actual weight, it's just that you don't feel it. So your apparent weight maybe is 0. It's because 20 minus 20 becomes 0. Okay, so with this in mind, we can say, we look at this diagram and the object is in static equilibrium. Of course it's not really static because it will keep on moving up and down, but we are talking about ideal state. Ideally speaking, they stop moving. Okay, going down is equals to moving up, so Fu equals to W obj. So you must remember these two formula very well because you are going to use this quite often. Okay, the weight of the liquid equals to weight of the object. So the next step is we want to find out what we can derive from here. Okay, we use another blank page. So we have this, W equals to obj equals to W equals to LIQ. So you have rho object, V object, G, and then you have rho object V. Now this liquid, and G. You see, you could actually cut off the G quite easily, and you have, I'll just write rho 1 V1 equals to rho 2 V2. Okay, we will find out some example calculation later using rho 1 v1 equals to rho 2 v2. Okay, before that we just go back to this. To prove that there's a force, there's a buoyant force or upthrust you like to call it, we want to investigate some element of water below the water surface. So at this point it is actually at the depth of HA, and at this point is at the depth of HB. You see, the pressure at A is actually higher than pressure at B, so the higher pressure would certainly push up the lower pressure at B. So the difference of pressure is higher minus lower, so you have PA minus PB. PA itself, if you can see from here, is rho GHA. PB, you can see it from here, is rho GHB. So PA minus PB is a rho G, and then you factorize, you get HA minus HB. Basically, difference of pressure lead us to a force here. Okay, this force is the upthrust, or you can call it buoyant force. Therefore, whatever Archimedes says is proven. Okay, there's an upthrust.